This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss the scoring guidelines for the 2018 AP Calculus exam free response question AB3 BC3. My name is Steve Kokoska. I'm a professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question and the scoring guidelines used at the AP Calculus reading. I'll present a brief general summary for student performance on this question. Then I'll consider more detailed interpretations of the scoring guidelines and how these guidelines were applied in certain situations. I'll consider some common student errors, and where appropriate, I'll present some specific scoring examples. This problem involved the graph of a continuous function g, the derivative of the function f, and the graph of g is given. In part A, we're given an initial condition, and we need to find f of minus 5. In part B, we need to evaluate a definite integral. In part C, we are asked to find the open intervals on which the graph of f is both increasing and concave up. And in part D, we need to find the x-coordinate of each point of inflection on the graph of f. Part A was worth 2 points. 1 point for writing the correct definite integral used in obtaining the answer, and 1 point for the final answer. Part B was worth 3 points. 1 point for recognizing and communicating that in order to evaluate the definite integral, we need to split it into 2 parts at x equals 3. 1 point for the antiderivative of the polynomial piece, and 1 point for the final answer. Part C was worth 2 points. 1 point for writing both correct intervals, and 1 point for providing a sufficient reason for choosing these 2 intervals. Part D was worth 2 points. 1 point for simply presenting x equals 4, and 1 point for a sufficient reason. Here are some general comments about student performance on this question. In Part A, there were some students who had trouble simply starting this problem. They didn't know where to begin. Some students seemed to understand the need to use the initial condition, but couldn't determine how to do so. Some students knew to use the definite integral, but did not know how to use the geometric areas to calculate a value. Now, many students used the geometry correctly. They calculated a correct value for the definite integral, but used the initial condition in a variety of incorrect ways. And some students actually attempted to solve this problem analytically by writing an algebraic expression for g. In Part B, many students had difficulty dealing with this piecewise defined function. Some used g of x equal to 2 times x minus 4 squared on the entire interval 1 to 6. Some students made an error in finding this definite integral. They computed this value as 5, probably incorrectly extending the lower bound to 0. Those students who were able to find an antiderivative were generally successful in this problem. And some students tried to solve this problem by finding a derivative of g. Most students were successful in Part C. Those students who reported only one interval most often wrote the interval 4 to 6 with a valid reason. Errors in the reason were most often related to the concavity of the graph of f. And there was some use of vague language here, references to the slope or the function. Students need to specify exactly which slope or which function they are referring to. In Part D, many students were able to identify x equals 4, but many had difficulty providing a valid reason. And the most common incorrect answer was x equals 3 and x equals 4. In Part A, the first point was for the definite integral. And here are some examples that earned the first point. Now, if the student did not present a definite integral, they could still earn this point by presenting enough arithmetic to convey the definite integral. And that means they had to present the area below the x-axis as the area of a square in a triangle, or as the area of a trapezoid, and show the area above the x-axis as the area of a triangle. And here are some examples. And here are some examples that did not earn the first point. In this case, the integrand is not the function g over the interval -5 to 1. And in this case, the arithmetic isn't sufficient to convey the definite integral. The second point in Part A was for the answer, 25/2, with supporting work, which may or may not have earned the first point. Here are some examples that would earn the second point. Remember, if a student links two unequal mathematical expressions with an equal sign, they do not earn the answer point. And there were other valid, perhaps longer, solutions to this problem. And these involved the use of a different initial condition, successive accumulations from x equal 1, or even an analytic solution, which involved finding an algebraic expression for g. Here are some example responses and how each was scored. The first example is a bald answer. There is no supporting work. This earns 0, 0. In example 2, there isn't enough evidence or communication of the definite integral. This earns 0, 1. In example 3, there is just enough communication of the definite integral. This earns 1, 1. In example 4, this is incorrect communication of the definite integral. They do not earn the first point. But the student could somehow put this together with the initial condition and earn the answer point. Example 5 earns 1, 1, and example 6 earns the integral point. In Part B, the first point is for knowing and communicating the need to split the definite integral into two parts at x equal 3. Here are 4 examples in which the student would earn the first point. Here, a must be a value between -5 and 3. And the two integrals do not need to be connected with an addition symbol. In example 3, the student has already computed the first definite integral. And in example 4, they may split the original integral into an additional expression. The second point in Part B was for the antiderivative of 2 times x minus 4 squared. Now, this has to be our antiderivative, and here are some acceptable responses. The student could also start this antidifferentiation with a numerical expression, that is, present no symbolic antiderivative. And here are some examples in which the student would earn the antiderivative point. The third point in Part B was for the answer, and there was an eligibility criteria here. The student must earn the antiderivative point to be eligible to earn this third point. This point was earned for our answer, 10. Now again, if a student presented a linkage error, they do not earn the third point. But there was one exception here, involving a U substitution. There were a few other issues involving a missing differential dx and some copy errors. And there were fair procedures in place for scoring these responses. Here are some example responses in Part B and how each was scored. In example 1, there is no split, but a correct antiderivative. This earns 0, 1, 0. In example 2, everything is correct. Even though there is no arithmetic presented, this earns all 3 points. In example 3, there is a correct split, a correct antiderivative, but a linkage error. This earns 1, 1, 0. In example 4, the 5 is incorrect, but this is sufficient evidence the student used the bounds 0 to 3. So they earn the split point and the antiderivative point, but not the answer point. And in example 5, there is no split point, but a correct antiderivative. This earns 0, 1, 0. In part C, the first point was for the correct intervals. Now, in this problem, the student may include or exclude the endpoints of the intervals, and various notation was accepted. Here are a few examples. Note, however, that the student could not present an endpoint explicitly outside the domain of the function g. The second point in part C was for the reason, and there was an eligibility criteria here also. The student had to present one of these items to be eligible for this point. They had to present the correct intervals, or exactly one of our intervals and a subset of the other interval, or exactly one of our intervals, or intervals of this form, where b is outside the domain of the function g. Note that only the first bulleted item here earns the first point. The remaining 3 items do not earn the first point, but the student is eligible to earn the second point. This point was earned for the correct reason, using f prime, g, and or g prime. And here are some acceptable reasons. If the student reasoned using f double prime, then they were required to explicitly state that g prime equals f double prime. And vague references to things like the function, the slope, the derivative, or the graph did not earn the point. In part D, the first point was for the answer. And here are some examples that would earn the point. In this case, a bald answer, x equals 4, earns the point. Note that any subset of those intervals were accepted here because there is some ambiguity in the definition of an inflection point. The coordinate 4, 0 did not earn the point. The second point in part D was for the reason. And the eligibility here was the correct answer. That is, the student earned the answer point, or they had the coordinate 4, 0. And here is a list of acceptable reasons. Here are some responses that did not earn the reason point. F changes concavity at x equals 4. G changes direction at x equals 4. And vague, nonspecific references to the function, the slope, or the derivative. I want to assure you that there were fair procedures in place for scoring those papers involving subsets of these intervals. And just a reminder, we don't penalize for spelling errors, like infection versus inflection. And we understand common abbreviations, like POI for point of inflection. At the AP Calculus reading, an actual briefing for the scoring of a free response question usually takes approximately 75 minutes. And there is also time allotted in the reading rooms for discussion before the actual scoring begins. However, I hope this summary video gives you a good idea of how this question was scored. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.